Okay, let's take a look at mass spectroscopy and average atomic masses. All right, so the things we're going to be looking at here is basically what I just said a minute ago. Mass spectroscopy, which is a measurement technique, and how mass spectroscopy can be used to determine average atomic masses. All right, so first of all, this is a mass spectrometer. It's a little bit small, so it might be kind of hard to see how this works, but a sample, and for our cases, let's say a atomic sample, sample of some element like chlorine or phosphorus or boron or something like that, enters through the left side of the chamber. This whole part, and here this whole part is under vacuum, so there's no air inside there. And the sample comes in as kind of a beam of gas atoms, and right in here there's a high intensity light source that knocks an electron off of the atom, so the atoms become ionized. So we start with some element in the gas phase, and as it passes through this little area in here, an electron gets knocked off, and so you end up with positive ions. And the ions continue through here, and then they go between the poles of a magnet here. And this part is not really part of chemistry, it's really part of physics, but a moving ion, or any kind of a charged particle moving through a magnetic field, gets a small force which causes it to deviate from its path. So the ions, as they move through this magnetic field, their paths curve and they separate out. And the way this part over here works, I like to think of this as kind of like a some kind of a Batman supervillain, maybe the Joker or something like that. And there's a road here, right? And the supervillain, the Joker, is standing over here with some kind of a magnet. And since it's a cartoon, the magnet's always going to look like that, right? That's how magnets always look in cartoons. And as vehicles come down the road, the Joker turns on the magnet and tries to cause the vehicles to veer off of their path, to crash or to capture the vehicle or whatever the heck kind of crazy scheme he's got going on. But if you had a large vehicle, you know, like some kind of a truck, you know, coming through here, the truck is so heavy that when it passes near the magnetic field, its path is going to curve just a little bit, right? But if you had a, well, I can't draw very well. If you had like a Volkswagen Bug, that doesn't look at all like a Volkswagen Bug. But if you had a Volkswagen Bug, it's much lighter, and so its path would curve a lot more. And if you had, say, you know, a motorcycle, it's lighter still, and so its path would curve even more. So the point is that just like the vehicles on this road here approaching the supervillain's magnet, the same thing happens over here, and that is that all of the ions, their path is slightly diverted by going through this magnetic field, but the amount that their path is curved, right, depends on the mass of that particle. So heavy ions are going to be deflected a small amount, and very lightweight or low mass ions are going to be deflected much more. And so if you look at this detector here, things that are hitting on that side of the detector have a large mass, things that are hitting on that side of the detector have a smaller mass, and you can measure the mass of all the different particles by where they hit on that detector screen. All right, so let's see what this would look like in real life. So here are a couple of mass spectra. This is the kind of data that you would get as a readout from that experiment that we're showing on the previous page. And so in chlorine, for example, this readout shows the mass of the ions here in atomic mass units, and percent abundance, that's how many ions there were of each particular type, right? So in chlorine, when all of the chlorine atoms get converted into ions and they hit the screen, most of them hit the screen at a spot that corresponds to 35 atomic mass units, and a few of them hit the screen at a spot that corresponds to 37 atomic mass units. And you can see, if you look on the vertical axis, that the ratio is about, maybe it's about 76% with the mass of 35 and about 24% with a mass of 37, right? So these atoms up here would be chlorine 35 atoms, and these down here will be chlorine 37 atoms. And the same thing is true if you look over here on the right. This is a mass spectrum of gallium, and you can see that just like chlorine, gallium also has two common isotopes. One has a mass of 69 and one has a mass of 79 or 71. And the ratios, it looks like there's about a 60-40 ratio of those two different ions, or excuse me, those two different atoms. They become ions in the mass spectrometer, but what we're really interested in is the atoms themselves, right? So there's about a 60-40 ratio of gallium-68 to gallium-71. All right, and then what we can do is, based on these mass spectra, we can calculate what the average mass of an atom is for any particular element. So the average atomic mass is a weighted average of the masses of the isotopes in that mass spectrum, right? And what we mean by a weighted average is that instead of just averaging, for example, chlorine, there were some atoms with a mass of 35 AMU and some with a mass of 37 AMU. If you average those two together, you get 36, right? But if you remember, the mass spectrum looked like this, and there were a lot of them with a mass of 35 and a much smaller number with a mass of 37, right? So we want to take this ratio into account when we do our averaging, and that's what's meant by a weighted average. So the way we calculate a weighted average is we average each of the masses, but we multiply each of them by the fractional abundance, right? And that just means like this 70% or 60% or 40%, but instead of putting it in as a percent, we put it in as a decimal. So for example, if something was 73.1%, the fractional abundance would be 0.731. If something was 49.6%, the fractional abundance would be 0.496. Basically just converting this decimal, or excuse me, this fraction into a decimal number. Right. And we do that for each of the isotopes. Both of the ones we saw on that previous page had two naturally occurring isotopes, but you could have 3 or 4 or even 5 or 6. Most of the ones you'd encounter, here in Gen Chem would have 2 or maybe 3, just because if you find one that's got 5 different isotopes, it makes the problem a lot more complicated without really making it any more useful or interesting, right? So normally keep it to fairly simple cases where there are just maybe two or maybe 3 different isotopes that need to be averaged together. All right, so let's take a look at one. All right, we want to calculate the average mass of chlorine. So we look at these 2 different isotopes, and if all you have is the mass spectrum, right, this little data here, then you can assume that the mass here for this one isotope is 35 AMU and the mass here is 37 AMU, right? Because that's going to be really darn close. And you can also look at these guys here and estimate where you think those ratios are. So you might think this is 78% and 22%, or 77 and 23%, or whatever. If you have a problem that looks like this, just estimate these percents as well as you can, and you can assume that the isotopic masses are 35 AMU and 37 AMU. Okay. Turns out for chlorine, we actually have really good data on this. And I want to go ahead and use data that goes out to 4 significant figures, because the data on the periodic table we're going to compare this to later also has 4 significant figures. Right? So it turns out that the isotopic abundance of chlorine 35 is 75.77%, and for chlorine 37 it's 24.23%. And the masses of the two isotopes are 34.968 AMU and 36.966 AMU respectively. Right. Now, like I said, if you don't have this data here, you can just use 35 and 37. You'll still get essentially the same results. But since we've got better data, let's go ahead and use the better data. Okay, so let's do our calculation here. Remember, average atomic mass is a weighted average. It's a fractional abundance of isotope 1 times the mass of isotope 1 plus fractional abundance of isotope 2 times the mass of isotope 2. And then if you have more, add those in as well. In this case, we've only got 2. Right. So our first isotope is chlorine 35, and that was, what was it? It was 75.77%. So we'll write that in as a decimal number, 7577. That's the isotopic abundance. And then we'll multiply it by the mass, which is 34.968 atomic mass units. And then we'll do the same thing for the second isotope, which is the chlorine 37, which had an abundance of 24.23%. We'll convert that to a decimal, 2423. And the mass of that isotope was 36.966 AMU. Right. And when we do the math here, we multiply this together. This gives us 26.4953 AMU. And this part over here gives us, let's see, 8.9569 AMU. And these should have 4 significant figures, right? Since we're doing multiplication here, we've got 4 sig figs here, 5 sig figs here, so that should be 4 sig figs. And then when we add them together, add these two things together, we get 35.452 AMU. And since this has significant digits going to the 10th place, and this has significant figures going out to the 100th place, we should make this our last significant digit. And so for chlorine, our average atomic mass would be 35.45 atomic mass units. Wonderful. Okay, and one of the great things about doing these atomic mass calculations is you can actually check your results, because this number, this average atomic mass, is one of the numbers that you see when you look at the periodic table. As I mentioned in the last video, periodic tables can vary, and sometimes they include crystal structures, sometimes they include electronic structures, and sometimes they include common ionic charges and all kind of crazy stuff. But what every periodic table has, what's common about all of them, is all of them will have these 3 things. They'll have the atomic symbol, they will have a number which is an integer, and like I said, usually that's the number in the largest font, and that is the atomic number or the number of protons. And then they'll have another number which is not an integer, some kind of a decimal number, and that number is the average atomic mass. And that's the number that we just calculated a minute ago. And if you check with the periodic table, you'll see you get exactly the same result over here, 35.45 atomic mass units. All right, so how is using the average atomic mass useful? All right, let's say we're going to look at two different questions related to these chlorine atoms, and I'll draw a distinction between the two of them. All right, and let's assume we've got a bunch of chlorine atoms here. They've been chosen completely at random, and we want to select one of the chlorine atoms and say what the mass of that atom is going to be. So remind ourselves of the calculations that we just did before. 75.77% are chlorine 35s with this mass, and 24.23% are chlorine 37 atoms which have this mass. Right? And the average is 35.45. Okay. So if we had a really tiny pair of tweezers and we reached in and just grabbed one of these things at random, what would the mass be? Well, we don't really know what the mass would be because we're selecting them at random, but probably, if we do this, about 76% of the time, the mass would be 34.968 AMU, right? Sometimes, about a quarter of the time, if we pull one out at random, about 25% of the time we would end up selecting one with a mass of 36.966 AMU. All right. So most of the time we'd get this mass. Sometimes we would get this mass. And this is the part that's important, that a lot of people get this wrong on questions like this. We would never pull up an atom with a mass of 35.45 AMU, because none of these atoms over here, none of the atoms have that mass, right? The average mass of all of those atoms together is 35.45 AMU, but none of these individual atoms actually has that mass. All of them have a mass of either 35 or 37. All right, so when is the average mass actually useful? We can look at a similar question. Instead of selecting one atom at random, what would we get if we selected 5,000 atoms at random? And again, we will remind ourselves of the data that we calculated from before. So we want to select 5,000 atoms at random, right? So the first question is, we know that some of them are going to have a mass of 35 and some will have a mass of 37. How many of them are going to have a mass of 35 AMU? Right? Well, the number that have a mass of 35 is going to be 75.77% of our total. Okay, so the number with a mass of 34.968 AMU would be 5,000 atoms times the percent, which is 77.77%, but we'll convert that to a decimal. Let's see what we get there. Okay, so we would get 3,000 788 atoms with a mass of 35.968 AMU. And so the total mass of these would be 3788. We'd have that many atoms, each with a mass of 34.968 AMU. And that would be big number, 132,459 AMU. All right, but we only got 4 sig figs here, so we should round that off there. Okay. But before we round it, so this is only a part of the sample. There is also a bunch of atoms with a mass of 37, or actually 36.966 AMU, and the number that would have that mass is just going to be 24.23% of our total, right? So number with that mass is going to be the total number of atoms, 5,000, times the probability of drawing an atom with that particular mass, which is 24%, but we're going to write this as a decimal number. And that gives us, let's see, 1,212 atoms with that mass. And so the total mass for all of these is going to be the number of atoms times their mass which is 44,803 atomic mass units. So the whole collection of 5,000 atoms together is just going to be this mass plus this mass, right? And if we add those two things together, we get 177,262 atomic mass units, and we probably want to round this to 4 significant figures based on our calculations here. So let's call this 177,300 AMU. All right. So that's a simple calculation, right? But it's really long. A whole bunch of steps worrying about how many atoms are going to have this mass and how many atoms are going to have this mass, right? Probably most of you are already a step ahead of me. There's a much easier way to do this. And the easier way to do it is to just look at this average mass here, right? And if we've got a single atom, then all we can use is the probability. Either it's going to have a mass of 35 or a mass of 37. But if we've got a whole bunch of them, then we can assume that the probability is going to kind of even out so that we'll get a statistically weighted sample, and about 76% of them are going to have this mass, and about 24% of them are going to have this mass, and so we can just use the average mass here, right? So a much, much simpler way to do it is just to take the number of atoms and use this average mass. And so if we do it that way, we can just say we've got 5,000 atoms, and on average, they have a mass of 35.45 atomic mass units. And when we multiply those together, lo and behold, we get essentially the same answer. This one would round to, I mean, it's right, it's right there. So it just barely rounds to a different number in that fourth significant figure, right? But essentially, those two things are the same. And so whenever you've got a large number of atoms, this is a much, much quicker and easier way to calculate the weight of that group of atoms, or the mass of that group of atoms. And that's useful to us because anytime you go to the lab and you weigh something out on the scale, anything that's big enough to weigh is going to have millions of millions of millions of atoms, right? So this statistical average can always be used for any sample that is macroscopic. Anything that's big enough to handle, you can use this average number instead of worrying about those two individual isotopic masses. Okay, so try this one out. Same kind of a problem. Here is a mass spectrum of gallium. So I'm not going to give you the exact numbers for this because frankly the math is easier if you just kind of round things. So just kind of look and see where you think those things are, and then you can just assume masses of 69 and 71 AMU. Go ahead and do the calculation, determine the average atomic mass of gallium, and then remember that that number is given in the periodic table, so you can flip to the periodic table and see what you get, see what it shows there for the atomic mass of gallium. Okay, hit pause and do the calculation, then you can check back and see what I got. Okay, so when I looked at this, I decided that this looked like it was about 60%, and this is about 40%. So I just used 0.60 and 0.40 for my isotopic abundances. And for the masses, I use 69 AMU and 71 AMU. When I do the math there, I get 41.4 AMU for all of the 69s and 28.4 AMU for all of the 71s. And when I add them together, I got 69.8 AMU for my average. And if you check the periodic table, my periodic table, for example, sometimes there are small differences in those last few digits because they get remeasured and they sometimes get revised. But anyway, the periodic table that I'm looking at has 69.72 AMU. Oop, left out my C, actual. Okay. So, even with this kind of crude reading of this graph and rounding these masses to integer values for the of 6971 AMU, even by doing that, we got a really good estimate of the average atomic mass here. All right. Okay, so we're going to look at another calculation in a minute, but one thing you should be able to do is use this equation to calculate average atomic masses, and the other thing that we're doing is you should be able to interpret these mass spectrum graphs. Okay, so those are the two skills that we've been working on. Okay, and also you should be able to use the average atomic mass if you calculate it like we just did on the last slide. And calculate the average atomic mass, you can use it, but also recognize that the average atomic mass is given to you in each of those little cells on the periodic table. And so you should be able to use the average atomic mass from the periodic table as well. Okay, so for example, if we are calculating the mass of 75,000 iron atoms, right, we can use that average atomic mass. So we just take 75,000 atoms and multiply by the average mass, 55.85 AMU, And when I did that, I got 4,188,750 AMU, which is god awful looking number, right? But for our significant figures, we've only got 2 significant figures here in the 75,000. If you wanted to think of that as a counting number, I guess you could call it 5 sig figs if you wanted to. But we definitely only got 4 sig figs here, so one way or another we got to round this a little bit. If you want to consider this to be 2 significant figures, then you would round this to 2 sig figs, and we can call this 4.2 times 10 to the 6 AMU. If you wanted to round it to 4 instead and call it 4.189 times 10 to the 6 AMU, you could do that. An argument can be made either way. But 4.2 million AMU. Now, for this one, we also want to calculate the result in grams, right? So we have to go back and remember that relationship between grams and AMU. And remember that relationship is given by Avogadro's number. And since we can write grams and AMU as being equal to one another, right? This is just a conversion factor, and we can make a fraction out of that, and that fraction is equal to 1, and we can use that to do our conversion. Okay. So I'm not going to round this to 2 sig figs at the beginning. I'm going to keep a few extra significant digits so that we do all of our rounding at the end, right? So I'm going to go ahead and write 4.188,750 AMU. And then we want to use this conversion factor. We're trying to get rid of AMU, so we want those units to cancel. So we're going to put that on the bottom. Okay. Also, before we do this, we can think about our result, right? 75,000 is a lot, but when we're talking about atoms are so very, very, very small. 75,000 is not very many atoms. And so when we calculate this in grams, we should get a really, really small number. So we want to check and make sure that when we do this, we have this fraction set up correctly so that we get a big number. If we did this part here wrong, we might get a result like, I don't know, something like 1.5 times 10 to the 20 grams. And that's like approximately the weight of the Earth or something, right? So that's got to be wrong. We want to always look at our answer and make sure that our answer makes sense. All right. Okay, so we'll check our units. Our AMUs cancel out. And if we plug this into our calculator, okay, I got 6.9557 times 10 to the minus 18 grams. Okay. And then we want to think about our significant figures. This number here only had 2 sig figs, so this number here should have 2 sig figs. So we'll rewrite that. I'm going to clear some of this out to make some space. Okay. All right, so we would rewrite that then as 7.0 times 10 to the minus 18 grams. Right. All right, and there's our result. Wonderful. Okay, so in this one we looked at mass spectroscopy. You should be somewhat familiar with that instrument and understand that the atoms go in, they get converted into ions, and then as they pass between the poles of that magnet, the ions are deflected, and the amount of deflection depends on their masses. And so when you look at where all of those ions hit on this detector, you can tell the masses of each of the different atoms and the relative amount of each kind. Right? You should also be able to interpret these mass spectra. Here's one with 3 different isotopes, where you have the percent abundance on the y-axis and the mass in atomic mass units on the x-axis, right? So you should be able to read and interpret those kind of spectra, the kind of mass spectrum data. Right? Then we used those data to calculate average atomic masses, and that's just a weighted average of the different masses of the naturally occurring isotopes. And we looked at using the atomic mass to calculate the masses of large collections of atoms. And you can do that either with the atomic mass that you calculate from isotopic mass data, or you can do it just by looking at periodic table, which will always give you the average atomic mass and a decimal number in each cell of the table. All right, terrific. There are a bunch of those in the study guide, so have at it and have fun.